Okay, so now we will start section 6.2, where we are going to solve initial value problems by using Laplace transform. But before this, let's review what we did until now. We learned that Laplace transform is an integral transform. So where you have a function in the time domain given which is defined for t bigger or equal to 0, then by using Laplace transform, then we get a new function in the S domain. So where we are using capital F. So we are given a function in the time domain, or you can consider as a signal, and then by using Laplace, the integral transform, we get a new function in the S domain. And the formula for this was given as from 0 to infinity e to the minus st. Remember, we call this the kernel of this integral transform, which will be a different function when we come to the different integral transform later, which we call as Fourier transform. So now, and since this was an improper integral, we also mentioned under what conditions this thing converges, and because if it doesn't converge, then there is nothing about the Laplace transform of that given function. And we said if it's an exponential order function, like if it is not faster than an exponential, then clearly we will have Laplace transform for a piecewise continuous function. So what was piecewise continuous? It basically, we will have discontinuities, but these discontinuities will be only jumps or removable ones, not the infinite discontinuities. So that's necessary to talk about integration, and convergence is necessary to talk about existence of such a f of s. So at least f of s must be defined on an interval to talk about Laplace transform. All right, so furthermore, like we learned Laplace transform of certain functions, 1, t to the n, e to the at, and also sine function. So let me say something. As I said, in the previous lecture, basically there's a table in page 252 in the 11th edition, and it is 317 in the 9th edition. So, and if you look at it, I will try to complete this table by finding the Laplace transform of these functions. We did the first one, we did the second one, we did the third one. I'm skipping the fourth one that's given as an exercise. So we did the fifth one. We will try to find the rest of it too. And now, so you can just put a cross or a check to the 1, 2, and 3, and 5. And actually, you can put a check to the sine hyperbolic and cosine hyperbolic because, they are defined in terms of exponential functions. So I may write in a couple of minutes. But first of all, I want to say something more about this Laplace transform before we start this differential equations. So the most important property maybe is Laplace transform is an integral transform, so it's a linear transform. So it's a linear operator. So, and that's what we said in the last 10 minutes of the previous lecture. So Laplace is linear, and so it's a linear operator. Then we can talk about the inverse of this linear operator, which will go back this way. So, which will be also, since L is linear, its inverse will be a linear operator. So what this means, a time domain, here you have a function, Laplace will give you a function in the S domain, and Laplace inverse, which is also linear, will give you an inverse. Since it's an integral transform, whenever you are working with continuous functions, this inverse is unique. Inverse is unique. So if you are assuming the function you are going to get is continuous, then inverse is unique. Otherwise, if you think about the Laplace transform of the constant function 1 everywhere, or the everywhere it's 1, except at one point they will have the same Laplace transforms. So if you assume continuity, then inverse is unique, so you can find it. So, and this L inverse is also linear. What I mean is, so let's say C times f of s plus d times g of s. Now, you are taking the inverse Laplace, so this is going to be C times L inverse of f of s plus d times L inverse of g of s. Okay, so inverse is unique. So this way, I mean, you can come back to the time domain. So this will be now, maybe you can call this like, this is f of t, and this is g of t. So how are we going to handle these things? Of course, I mean, we will go back. At some point, we will use our memorization because we know certain formulas. So if you want to see some examples, for example, Laplace inverse of 4 over s minus 2. Now, 4 is not important here because you can always take it out from this property. So this is 4 times the Laplace inverse of 1 over s minus 2. And we know from our previous calculations, this is basically the 1 over s minus 2 is the Laplace of e to the 2t. So now then this is going to be 4 times e to the 2t. This is what we have. So how did I conclude this? Because I knew this. So I'm just basically going back. So if you are going back, you have to know certain things. Otherwise, I mean, you will get lost. And basically, I mean, somehow we are memorizing the things in the table. And after doing tons of examples, I mean, automatically they just come to your brain and they are there. Okay. Now, let's do maybe one more example, which is more complicated than this one for the inverse. And then we can start this solving initial value problems. Another, maybe, let me just name this as 1 and name this as following. So s over s squared minus 1. How about the Laplace transform, inverse Laplace of this? Okay. Again, remember the motivation for the Laplace transform. So the Laplace transform, you had functions. We had complicated functions like exponential sign, complicated means, like not algebraic, basically, in this sense. But then, if you look at the Laplace transform, they became algebraic. They were all partial rational functions. So, and for the rational functions, I can write them as in the simplest partial fraction forms. And so, if you look at the Laplace of 1, t to the n, e to the at, and they were all simple like blocks, I mean like some building blocks for the rational function. So they were like in the partial fraction form. So whenever I am given this, so if you look at this one, this is a rational thing. So I can easily write this thing, as we know from the calculus courses, I can write this thing in the following way. S minus 1 s plus 1, which is the factorization of the denominator, since these are degree 1, so that I can find some a and b here, and this thing can be written in this way for the suitable a and b. So I can always express this rational thing in the following form. And now I know the inverse of these things, because if you forget about a here, this is 1 over s minus 1, and I know that this is the Laplace transform of e to the t. And if you look at forget about b, this is 1 over s plus 1. This is the Laplace transform e to the negative t. So that means as long as we can find a and b, I can easily find the Laplace inverse of these things. So, I mean, we can easily do this thing. So, all right. So, I mean, at this point, let me just write in the following way: a L inverse of 1 over s minus 1 and b L inverse of 1 over s plus 1. So whenever you find these things, then you can get it. Okay, so I'm leaving finding a and b to you, so because they can easily be computed. So that means then now for such an expression, then I can easily write this way and do. So don't worry, we will do more complicated examples than these, but the idea is, like, for the simple things we know the answer because we already know where they came from, and for non-simple things like these, so we will basically use the partial fraction method to separate it into some like a block in the building blocks, and then we will take the inverse of each because we know the inverse of each things separately. But the main motivation is partial fraction thing because we know where they came from. All right, now differential equations. So how are we going to solve differential equations by using the Laplace transform? First of all, we should know how to transform the derivative because we are taking derivatives in the differential equations. All right, so now for this I will state a theorem and which will just tell us how to transform the derivative. And also by using this we will be able to transform the first derivative, second derivative, vice versa. So what does this theorem say? Suppose that now, similar to the existence problem, we now have f is continuous and its derivative is piecewise continuous. So I'm writing cont, which means like continuous, and on any interval 0, a. Okay, so for any a, of course. Now, this is somehow like integrability condition, so we can integrate f prime, we can integrate f. Second, and f of t is less than or equal to k times e to the at for t bigger than m for some positive a, k, m. So which are some positive real numbers. Okay. Now, then Laplace transform of the derivative of f exists, and Laplace transform of the derivative of f is equal to. Now let's leave this part blank, like the I don't want to ruin this prize. So what is this going to be? So, but at least, I mean, this thing says that, yes, derivatives will have a Laplace transform too. So if you remember the previous theorem, in the previous theorem, we were assuming f is continuous, f is piecewise continuous, and this means like f is an has an exponential order. It's not faster than an exponential. So this thing guarantees f is continuous, so it automatically piecewise continuous. And this condition says that f will have a Laplace transform. But furthermore, this theorem says that f prime is piecewise continuous with this condition somehow, then f prime will also have a Laplace transform. Then there's a formula for the Laplace transform of f prime. So we will now find it. Okay. So how is the proof done? So let's see now. So proof. So it's all about this integral now. First of all, I have to handle this. I have to handle this integral, and eventually I will take the limit as a goes to infinity, which will give me the Laplace transform of the derivative. But between 0 and a, f prime is not continuous, it's piecewise continuous. Piecewise continuous means it will have at most jump discontinuities. All right, so then at the jump discontinuities, finitely many, so I can write my integral just in the following way. So from 0 to t1, e to the minus st f prime t dt, plus from t1 to t2, e to the minus st f prime t dt. So this will continue until the last point where our function is not continuous. Let's say it is t, let's say n, to a e to the minus st f prime dt. So I separated my integral by using this points t1 to tn where our function is not continuous. So at ti, where I is between 1 and n, f is not continuous. But we know that at most jumps, removable, allowed, jump is fine, but no infinities. Okay, then now how can we compute? Of course, I mean, this is a product, so we can use integration by parts again. So if you use integration by parts, now this time I will choose this as my u, this as my dv, because I can automatically find v, which is going to be f. So with respect to this now, if you write this thing, then we are going to get the following. So we will have u times v. A u is this one, e to the minus st, and v will be f of t. And from 0 to t1 plus, I'm just grouping all of them. Let's take the uv for this one. This is going to be e to the minus st f of t from t1 to t2. And finally, e to the minus st f of t from tn to a. This is the first portion now, plus, minus the v du part. V is now f. What is du? If you take the derivative of this, then there is an minus s coming, because I'm taking derivative with respect to t. So there's a minus s coming, and there's another minus here. So this will be then plus s parentheses. What is inside now? V times du. Now v times du for this one, v times du for this one. So I will just write these things again. Now from 0 to t1, e to the minus st f of t dt, dot, 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 dot. Let me just write the last one, from Tn to a e to the minus st f of t dt. Now, if you look at these things, suppose we computed them. So there is e to the minus st f of t at t1. It will come here. But again, the same thing will come here too. But there will be a minus in front of this. So plug in t1 here, plug in t1 here, because of minus in front of that, they will cancel each other. So now t1s are cancelled, t2 will be cancelled with the following one. So this will continue, there will be cancellations, and tn will be cancelled by using the previous one. So what is remaining? Just this a is remaining, and this 0 is remaining. So then what do we get out of this? We will have e to the minus s times a f of a, and minus, because this now it is the bottom boundary, so if I plug in 0 here, then if I plug in 0, this is f of 0, e to the 0 is 1, so we have f of 0. Similarly, it will happen for this one too. Suppose you computed this integral. In the following one, there's a t1. In the following one, there is a t1, and so they will cancel each other too. And t2 will be canceling again the value. So tn until tn, everything is cancelled. Then what is left is just the following. This can be written as plus s, just then I can just write, maybe they cancel. So I can write this thing in just one formula as from 0 to a and e to the minus st f of t dt. Again, there will be cancellations, but I'm just grouping them again. This time I'm not doing the cancellation actually, so I'm just rewriting it. So this is just an integral from 0 to a. I'm rewriting it. So I didn't compute anything there. So this is what we got. So then what's going to happen? What's going to happen here? So eventually I will take the limit of this, and I will take as now the a goes to plus infinity. I should say something about this one now. I don't want to write it, so I will just say it verbally. Now, I want this thing to converge. Now, if you look at, as a goes to infinity, if you look at this portion, there is no problem for this one because this is exactly the same as the Laplace transform of f of t. And from the requirements, f is continuous and f is exponential order. From the previous theorem, we know that this exists, and which is going to be the Laplace transform of f. As a goes to infinity, this will give us the Laplace transform of f times s. Okay. Furthermore, now I want this part to converge. F of 0, it's known because f is a function starting from 0, so there is nothing here. Now this must converge. Again, now what we have here is so f of a e to the minus sa. Again, exponential either will go to infinity or it will go to 0. If it goes to infinity, and f of a, if this goes to infinity, there is nothing to stop. So then only if this part goes to 0, then this may go to a number, this may go to, it may go to 0, it may go to infinity, whatever. In any case, like this must go to 0. If this goes to infinity, then there is no way we can stop this. So that's the reason this must go to 0. In that case, so I can take it down again, f of a over e to the sa. Now I have to look at this quotient's limit. So if the top goes to number, bottom goes to infinity, then there's nothing to worry because it will go to 0. If the top goes to infinity, bottom goes to infinity, at this point again we can use L'Hopital's rule. For the L'Hopital's rule now, actually, I mean, f is continuous, so if f were differentiable, I could easily use L'Hopital rule and evaluate. This is what's happening in the usual problems. But if f is continuous, so top goes to infinity, bottom goes to infinity. But we have the following thing here. So f is less than an exponential when t is bigger or equal to m. So eventually, which will make this thing tending to 0. It will pushing it to the 0. Okay? So that's why then this will go to 0. Because here small a is constant. It's not changing. But in this case, this is now. And so if you just imitate the previous proof we did, there's just a small shifting. You can read from the book. And then this will also go to 0. So eventually, this part will go to 0. This is just f0 value. And this is the Laplace transform of the f function. So then the formula says that we have s times the Laplace transform of f minus f of 0. So this is s times the Laplace transform of f minus f of 0. This is what we get. All right. So now we know how to transform the derivative. Now how to transform the second derivative, a third derivative, fourth derivative. And so we can imitate the same theorem. And we can do more and more. In that case, let's talk about, I want to find the second derivative's Laplace. Then so in this case, I can state the theorem in such a way that I can guarantee the Laplace transform of f. So what I can do is the following. Now, let's talk about the second derivative. So if I assume that f is a nice function, f prime is continuous, f double prime is piecewise continuous, and f again satisfying such a property, then in that case, we can easily prove that the second derivative will have a Laplace. So how will I get it? Of course, it will relate it to the previous one because second derivative is the derivative of the first derivative. So in that case, I didn't write it rigorously, but I'm just saying right now. So in that case, the second derivative's Laplace is going to be s times first derivative's Laplace minus just f prime 0. That's how it's going to be related. So second derivative is related to the first derivative. But now I know this because I know that under these conditions f will have a Laplace. So I can rewrite it by using the formula here. Sorry. That's. And so if you expand everything, then what do we get? We get s squared Laplace of f of t minus s times f of 0 minus f prime 0. Now, you can do it for the third derivative. You can relate the third derivative to the second derivative. And of course, you are assuming third derivative is piecewise continuous. The previous ones are, continuous or nice, like differentiable. And so if you want second derivative to piecewise continuous here, then first derivative must be continuous. So then you can have f differentiable, so we can go this way. So now we found second derivative. So clearly, I mean, we can write a formula for the nth derivative. Let me write it. I erased it. Let me write it rigorously so you can follow this. So it's coming from just the previous one. So corollary is just a simple conclusion we will get from the first one. So suppose that suppose that f prime f n minus 1 derivative, all these things are continuous. And f n derivative is piecewise continuous on 0a for any a positive. Again, the second condition is f is less than or equal to k times e to the at, where t is bigger or equal to m for some a k m positive. Okay. Then Laplace transform of the nth derivative exists, and it's given by the following formula: the nth derivatives Laplace. So you can look at the following here: s squared times Laplace of f minus s times f of 0 minus f prime 0. So this is for the second derivative. Second derivative, s squared. And if you look at the powers of s squared, they're going s squared minus s to the 0, which is 1. So if you do this thing, then we will have s to the n Laplace transform of f minus s to the n minus 1 times f of 0 minus s to the n minus 2 times f prime 0 minus minus eventually you finish with n minus 1 derivative at 0. So this is what we have. So that's the reason now, as you can see, when we are finding the Laplace of nth derivative, so we need some initial values. That's the reason if you are going to solve differential equations, then you must have some initial values so we can transform our derivatives. Okay. All right. Now, let's do one simple example for this. How about the Laplace transform of cosine AT? Now, let's find this. I know that cosine is a derivative of sine. So I can write this thing in the following way. sine AT's derivative. But if I take the derivative of sine AT, then I get A times cosine AT. So if I divide by A, then now insides are equal. Derivative of sine AT is cosine AT times A. This A now cancels. I get the same thing. Now, so constant A, linear property says you can take it out, 1 over A, Laplace of sine AT's derivative. So, sine AT's derivative. Now we can use the formula. This is 1 over A now there. S times Laplace of sine AT minus sine A at 0. Sine A times 0. So this is like your f prime. F prime's Laplace is equal to S times Laplace of f minus f0. So then what do we get? We have 1 over A S times sine AT's Laplace. We have A over S squared plus A squared. Sine 0 is 0, so this is 0. And so what do we get? A's are cancelling. We have S over S squared plus A squared. So Laplace of cosine is S over S squared plus A squared. Remember, Laplace of sine was A over S squared plus A squared. All right, so that was another formula in the table. So if you look at the table now, we also finished number 6. All right. I'm assuming, like, I mean, we finished number 7 and 8 because we know that cosine hyperbolic AT and sine hyperbolic AT, they can be expressed in terms of e to the AT and e to the minus AT. Okay, so this is e to the AT plus e to the minus t over 2. This is e to the AT minus e to the minus AT over 2. So since these are expressed this way, so it's just linear combination of e to the AT and e to the minus AT. Now I can easily take the Laplace transform of these, so which becomes 1 over 2 parentheses 1 over s minus a plus 1 over s plus a. So if you just put them together, you get s squared minus a squared in the denominator and the number in the numerator. So you can easily write these things. So that's the reason. If you look at the table now, we finished the 1, 2, 3, 4. I'm skipping it. It's gamma function. So there's an exercise, a nice exercise in the book. You can follow it, which is just generalization of the factorial. We now finished 5 and 6 and 7 and 8. And actually we finished 9 and 10 because we know that when you multiply a function with an exponential, it is shifting in the S domain like we did last time. So we did now 9 and 10. So we finished the first 10. So then we will come to the 11, 12, 13 and later. But I can do 11 today at the end of the lecture. Okay, now we use the derivative business to find the Laplace of cosine. And also, meanwhile, we gave something about hyperbolic functions. Okay. How about differential equations? Okay. Now, differential equations. So I want to do an example. But before this, let me fix the notation. So in our examples, we are using y prime, y double prime for the derivative. So that's the reason now for y of t is Laplace, I will write y of s. This is my notation, okay? And also, in our derivatives, I mean, we never write t inside, but we know that they are functions of t or functions of x, depending on the problem. So here we are using t as our variable, so I will fix this. So Laplace of y is the capital Y with variable s. Okay, now let's do an example. Solve y double prime plus, so let's do simple version maybe, y prime plus 2y equal to e to the minus t, and y0 is 0, y prime 0 is 1. Okay, so let's solve the differential equation. Actually, I will do this problem in two ways. First of all, we know that this is constant coefficient second order differential equation where on the right hand side you have an exponential. Clearly, you can solve this problem by using the characteristic polynomial, and since it's an exponential, you can find the particular solution by the method of undetermined coefficients. So I will first of all do in the typical way. And then I will solve the same problem by using the Laplace transform. And I'm going to time them. So I will see in how many minutes I will solve the first one, in how many minutes I will solve the second one. And after this, we will decide about which method is better. Okay, let's start. Okay, so let me just do my timing. Okay. So I'm starting now. All right, so for this problem, the characteristic polynomial is lambda square minus 2 lambda plus 2 equal to 0. And if you look at it, this one, this is lambda minus 1 square plus 1 is equal to 0. So from this, lambda minus 1 square is equal to 1 minus 1. So from this I understand that I will get complex roots. So my roots are 1 and 2. We can clearly use the discriminant formula. So if you take the square root of this, you get an I. So plus minus I. And if you put this thing on the other side, we have 1 plus minus I. So these are the things. So I have complex roots. I can clearly write the homogeneous solution, which is going to be C1 times e to the t times cosine t, because the coefficient here is 1, C2 times e to the t times sine t. Okay, now homogeneous part is done. Now, how about the particular solution? So this time I will not use the operator method or the annihilator method. I will just guess the particular solution. So on the right hand side I see an exponential. So, and if I'm going to get an exponential, plug into the derivatives, so then my particular solution must be an exponential, but I don't know its coefficient. So which exponential then I should try? The y particular, so it must be, of course, e to the minus t. I should try this one, because if you try e to the minus 2t or something else, then whenever you take the second derivative, first derivative, you will never reach to the e to the minus t. But I don't know the coefficient of this one. So that's the reason it's undetermined coefficient. I don't know its coefficient. So now this is our guess for the particular solution. So let's plug in this. So I need its first derivative, and I need its second derivative. So if you compute for the guess, we have minus a e to the minus t, and if you take one more derivative, we have a square e to the minus t. So now if you plug this thing into the, I'm sorry, this is not a square, this is plus a. If you plug this thing into the equation, the second derivative, we have a times e to the minus t minus 2 times the first derivative, which is minus a e to the minus t, plus 2 times y particular, which is a e to the minus a t. So I want this thing to be equal to e to the minus t. So if you do here, we have 2a, and a, so 5a is equal to e to the 5a e to the minus t is equal to this. So from this, we clearly see that a is equal to 1 over 5. So our general solution is then c1 e to the t cosine t, c2 e to the t sine t, plus 1 over 5 e to the negative t. So we found the general solution now. So what I'm going to do, I will plug in the initial conditions. Okay, so the initial conditions. Okay, so the first initial condition says that when you plug in 0, I erased the problem, so you can read from here, y0 is 0. So if you plug in 0 in your general thing, so cosine 0 is 1, so we get c1. Sine 0 is 0, so we have 0. And we have e to the 0 is 1 plus 1 over 5. So this c1 plus 1 over 5 must be 0, which says that c1 is equal to negative 1 over 5. And then now, I need the general derivative at 0, but let's first of all take the derivative of this, because I'm going to plug in 0 and I need to get 1. If you take the derivative of this, we will have c1 parentheses e to the t cosine t, and plus, so minus e to the t sine t, plus c2, and we will have e to the t sine t plus e to the t cosine t, and we will have minus 1 over 5 e to the negative t. So in this thing, if you plug in 0, then we must get 1. So if you plug in 0 here, sine 0, so this is 1. So we have c1 times 1. And again, sine is 0. We have cosine here, which is 1, plus c2. And if you plug in 0, we have minus 1 over 5. So this summation, it must be 1. And we know that c1 is negative 1 over 5. So this part is going to be negative 1 over 5. So then together we have negative 2 over 5. So if I want to reach to 1, then c2 must be 7 over 5. So c2 is 7 over 5. So now we can finish the problem. So the solution we are looking for is negative 1 over 5 times e to the t cosine t plus 7 over 5 e to the t sine t plus 1 over 5 e to the negative t. So I'm done. So let's look at the timing. So I solved in 7 minutes. But of course, I mean, I could do faster, but at the same time I am talking. Okay, so approximately 7 minutes. Okay, so we know the solution now. Let's do the same problem by using Laplace transform. So now what will I do? Second method, Laplace. So I will apply Laplace to the differential equation and see what's going to happen. So I'm taking the Laplace of both sides. So I will have my y prime plus 2y and e to the minus t. So remember the initial conditions. y0 was 0, y prime 0 was 1. Keep this in mind. So I will take the Laplace of both sides and then try to compute it. Okay. Okay, so let's time this one now. So I spend 1 minute here. And so then if you look at the second derivative's Laplace, keep in mind we use the following notation. Small y's Laplace is capital Y. So second derivative's Laplace. This is s squared y of s minus s times y0 minus y prime 0. Let me rewrite. Okay. Laplace of y of t, or just y, is equal to y of s. Now second derivative is this, minus 2 times y prime's Laplace, which is s times y of s minus y0, plus 2 times y's Laplace, because Laplace is linear, so we have y of s. On the other side, Laplace of e to the minus t, which is 1 over s plus 1. Okay. So now if you look at these numbers, y0 is 0, y prime 0 is 1 from the initial values, and y0 is 0 again. So now, then what is left? So there are terms containing y of s, there are terms containing just numbers. So let's group the y of s terms. Let's take y of s parentheses. Then what do I have here? I have an s squared minus 2s and plus 2. And there are some other terms. This is 0, this is minus 1, and this is 0. There is minus 1 here. And so let me put this minus 1 to the other side. So then what do we have then? I have 1 plus 1 over s plus 1. This is what we have. So if you look at, when you took the parentheses of y of s, inside actually you see the characteristic polynomial written this time in terms of s, not lambda. So then I can write now y of s. So then what is y of s? Y of s is equal to y of s is equal to 1 over s squared minus 2s plus 2 plus 1 over s plus 1 s squared minus 2s plus 2. So I solved the problem. No, just kidding. Yes, I found the solution, but I didn't find the y of t. I found the solution's Laplace. So this is the solution's Laplace, not the solution. So what do I want? I want y of t, the solution, the unique solution I am looking for. So I need to take the inverse Laplace of this. So I need to take the inverse Laplace. So again, now what we are going to do, these are partial fractions. We are going to find the inverse Laplace of each one, because we know that inverse Laplace is linear. So I have to do this one, I have to do this one. So let's start with the first one. So I have to rewrite it as something known, so I can take Laplace. So the first thing I will try, can I factorize it? As we know, I mean, actually, I'm just copying from the previous solution. There is no way we can factorize it because its roots are complex. So in the reals, we cannot factorize it. And we know that from the partial fraction method, if you cannot factorize, you can write it as sum of squares. Actually, like the one I did. So if you remember how the characteristic polynomial is written, this is s minus 1 square plus 1 square. So I wrote this as the sum of squares. Now, does it look something known? Actually, if you look at, if there wasn't 1 here, this is 1 over s square plus 1 square. If you remember the formula for sine, a over s square plus a square. A, s square, a square. So it makes, which means that, yes, it's actually sine. But there's a minus 1 here. So what's happening? We have s minus 1. And we know that there's a shifting in the s domain. If there's a shifting in the s domain, that means there's an exponential multiplication in the time domain. So then, if you apply inverse Laplace to this, this is actually, if you forget about this, we have 1 over s square. This is, it would be sine t if there wasn't any 1 here. But because of this 1, there's a shifting, which means that I have to multiply this with e to the t. So how do I find it? Again, forget about the shifting, erase all the shiftings, and look at the simple form. It is sine t. But there's a shifting. How do you arrange in the time domain? You have to multiply with the right exponential. Here shifting is one amount, so it is e to the 1t. Okay, so this part is done. Now let's come to the second part. Now second part can be factorized. How come? So s plus 1 s squared minus 2s plus 2. Okay, and this is okay, let me write this. A over s plus 1 plus, since this quadratic cannot be factorized, I have to write s squared minus 2s plus 2, and in the numerator there must be a degree 1 polynomial, so which is bs plus c. Now I have to compute a, b, and c, which will give us the equality. So what are we going to do? I know, maybe you know some tricky method, but I will just follow the regular method. So what will I do? I will multiply this thing with s squared minus 2s plus 2. I will multiply this thing with s plus 1 and try to equate the numerators, because now our denominators will be the same. So if you do this thing, we have s squared minus 2s plus 2 in the denominator. So what do we have in the numerator? So if you look at, we have as squared and here bs squared. So we have s squared terms with its coefficient is a plus b. Now how about the s term? What is the coefficient of s? So how do you get s? We have here a times minus 2s, so we have a minus 2a. And then if you multiply them, we have bs times 1, c times s. So bs, cs. So we have plus b, let me just write it better way, plus cs. Now, how about the constant term? We have here 2 times a common constant, and here we have c times 1 coming as constant. So we have 2a plus c. And from this now, I will get the following equalities. Now, if you look at this thing, so now on this side, we have just constant 1. On this side, we have tons of things. So coefficient of s square must be 0 because there is no s square there. Coefficient of s must be 0 because there is no s there. 2a plus c is constant. So the constant is 1 there. So I must equate them. So if you look at these, I get the following thing. A plus b must be 0. And minus 2a plus b plus c is equal to 0. And we have 2a plus c is equal to 1. So this is what we have here. All right. And so from this, a is equal to, or b is equal to minus a. B is equal to minus a. So if you put this thing into this one, so what do we get? We have minus 3a and plus c is equal to 0. And we have 2a plus c is equal to 1. So if you multiply the second one with minus and add them up, then what do we get from here? We have minus 5a is equal to minus 1. So a is equal to 1 over 5. So a is equal to 1 over 5. Then b is equal to minus 1 over 5. And then what is c? So if you look at from the last equation, c is equal to 1 minus 2a. So this is 2a is 2 over 5. If you subtract from this, you get 3 over 5. Okay. Now let's go back to the constants. So now this a is 1 over 5. B is minus 1 over 5. And C is 3 over 5. So now I have to find their inverse Laplace transforms. So let's do it here. So you can follow from this one. Just keep this in mind, e to the t. So the first one is easy. So Laplace inverse of 1 over 5 s plus 1 is, so this one, I'm taking inverse Laplace of this. So maybe let me remind you, Laplace inverse of this thing is equal to Laplace inverse of this one plus Laplace inverse of this one. So I will do this thing first and then this thing second. So then I will add them up. So if you do this, 1 over 5 comes out. And this is the same thing as e to the minus t. This is what we have. All right, now second one, this ugly one. How about this thing now? How about this one? So Laplace inverse of minus 1 over 5 s plus 3 over 5 over, I know this one, I can easily write this way, s minus 1 square plus 1 square. Okay, so if you look at now, I can separate this thing in the following way, and minus 1 over 5 inverse Laplace of s over s minus 1 square plus 1 square plus 3 over 5 Laplace inverse of 1 over s minus 1 square plus 1 square. Okay. All right. Did I make? Let me just check something. I mean, did I make any? 6 so far. Wait a minute. So let me just check my calculations. 2a plus c is 1. So 2 over 5, 3 over 5. So it becomes this. So minus 3a plus c. b is minus a, so minus 3a plus c. So we have minus 5a is equal to minus 1. Okay, so a is 1 over 5, so b is that one. Okay, it seems fine. All right. So how about this one now? Okay, so unfortunately, this is getting uglier, but we can do it now. So again, we have to use somehow like the table. So if you look at this, we did this one before, because if you look at the first thing we did was inverse of this. So I can easily write this. There is no problem. So this one was equal to e to the t times sine t. It was the same thing now. So now how about this one? But if you look at, there's an s here. So there's an s here. S square 1 square. So if there wasn't any shifting here, this will be cosine. But there's a shifting here, 1. So that means then in the time domain, you have to multiply with exponential e to the t. But if I do a shifting in the s domain, that means all the s's will be replaced by s minus 1. But one of them is replaced, the other is not. So then what am I going to do? So I should do a manipulation for this so I can use the table. So if this was s minus 1, now clearly you can see that s over s square plus 1 square, which is cosine Laplace, and there's a shifting applied in the s domain. So I'm done, but I'm changing the problem, so I have to correct it. So I subtracted 1, I have to add 1 to this. Now this is the same thing. So I can do them separately. S minus 1 over this plus 1 over this. But 1 over this is the same as this one, nothing changed. So that means there are two things coming here. The first one, minus 1 over 5, parentheses. So s minus 1 square, 1 square, which is shifted cosine. And so in the time domain, there's an exponential coming, which is e to the t. So cosine t. So this is plus e to the t sine t. So we found all the pieces. Now we can write the solution. Y of t. The first one we did was this in the previous one. So we had e to the t sine t. This is what we had. And then we did this one, which is 1 over 5 e to the minus t. And then now these things, which are minus 1 over 5 e to the t cosine t, minus 1 over 5 e to the t sine t, plus 3 over 5 e to the t sine t. Then what do we get? So if you look at this one, so this is e to the t sine t 1, and you subtract 1 over 5, but you add 3 over 5. So basically you are adding 2 over 5, which says that the coefficient of e to the sine t is 7 over 5. Okay, then the coefficient of e to the t times cosine t is just minus 1 over 5, and the coefficient of e to the minus t is 1 over 5. If you look at this, these are the same coefficients, and basically this is the same solution as we found by using the method of undetermined coefficients. Now let's look at the time. Oh, it took 20 minutes for me to solve these things, so now I can stop it. So which one? I mean, the previous one I solved in 7 minutes. Now this one I solved in 20 minutes because I had to do all these correction things and finding the A's and B and E's. So which one will we prefer? Of course the first one. The first one is easier and method, and we can solve by using that one. Then why are we learning this? Okay, then there is no need to learn the Laplace transform because we didn't gain anything. So it's over for the Laplace transform. We can just start the chapter 10. Now, of course, I'm just kidding. Then you understand, yes, Laplace transform is another method to solve this thing, but especially for such a problem, Laplace transform is applicable, but the other method is actually faster for us. Then you will not prefer Laplace transform for such a problem. Then why are we learning Laplace transform? The power of Laplace transform is basically comes from not for this kind of applications, it comes for some other things. So what are the other things? So if you look at this, in this problem, I had the problem second derivative minus 2y prime plus 2y is equal to e to the minus t. So on the other side, I had e to the minus t. So that, remember, if you just use the similarity with like mechanical problems like m y double prime plus gamma y prime plus k y. So, and the other side, there was a forcing function. So there's a forcing function, and you apply basically external force. In this case, is like, I mean, your external force is e to the minus t, and e to the minus t is a continuous function. And for a continuous function, undetermined coefficient solves faster. But if your force was not a continuous function, so if it was a piecewise continuous function, like let's say you apply a constant force 1, and then after 2 minutes you apply force 2, and then you apply 0 force, you apply an increasing force. So when you had a piecewise continuous function, then what would you do? Of course, in that case, you have to separate the solutions. You have to do between 0 and 1, between 1 and 2, between 2 and 3, or whatever where the piecewise, where the discontinuities are. So that in that case, after doing case by case, and after this, you will find one solution between 0 and 1. You will find another solution between 1 and 2. But then you have to glue them so that they are like, you have to match them so that the solution will be continuous. And so solve them and arrange the matching, so you will solve some equations to make the function continuous. So then it will take more and more time. But in that case, if you try to do the same problem by using the Laplace transform, it is faster. That's the reason the power of Laplace transform is basically coming from this. If the forcing function is a discontinuous function at certain points, like if it's a piecewise continuous function, then Laplace transform solves it in a faster and a smoother way. So that's the reason we will see that in the upcoming lectures. So first of all, we will learn how to write piecewise continuous functions, Laplaces, how to compute them, and then we will apply Laplace transform to solve these kind of problems where the forcing functions are piecewise continuous. Even we will see where the forcing function is not actually a function, kind of function you understand from calculus. Okay, now I'm finishing the second lecture. But before this, let me finish one more property as I promised. That property was the 11th property. When you multiply a function with t or t squared and t cubed, then what is the effect of this on the Laplace transform? So let me do this thing very briefly, and then I'm going to finish it. Okay, so example, let me just write this way. What is the Laplace transform of t times f of t? What is this equal to? So we know that this is from 0 to infinity e to the minus st times t f of t dt. But now, how am I going to find this? I mean, it's more complicated. So somehow, I mean, our experience says that I must relate it to some f here. Okay, now what was f of s before this? If I say like f of s is now the Laplace of this e to the minus st f of t dt, which is the Laplace transform of the small f. So I will cut the story short. So it's a function. It's defined by using an integral, so it's a nice function. So by using kind of fundamental term of calculus kind of business and using some advanced calculus, I want to take the derivative of this. If I take the derivative of this now, I'm skipping details here, so I will take the derivative of this one. So I will take the derivative of this. So be careful, I'm taking derivative with respect to s because my function is function of s. So now some advanced calculus rule says that you can take the derivative inside under certain conditions, and it's one of these things because I know this thing is convergent, vice versa, everything is nice, so I can take the derivative inside. But when you take the derivative inside, this function is if you look at everything, it's a function of s and t, and I'm going to take the derivative with respect to s. Okay. So then from 0 to infinity, I will take the derivative with respect to s. So I wrote the partial derivative because inside depends on s and t, f of t dt. So if you take the derivative with respect to s, be careful, I'm taking derivative with respect to s. Now t is like my coefficient here, so t minus t will come. So then what do I get? From 0 to infinity, e to the minus st t times f of t dt. So what did I get now? If you look at derivative of f, the capital F is equal to minus e to the minus st t times f of t from 0 to infinity. But it's the same thing except minus. So this is equal to negative f prime of s. And then you can do the following. I mean, you can take one more derivative. If you take one more derivative, second derivative, then you will take the one more derivative, and then what will come here? T square. Minus t plus t square. And so then you will have second derivative here when you multiply with t square. And so when you multiply with t cube, actually you can achieve it when you take the third derivative. And so this way you can follow it. And now let's write the formula as in given 11, or is in given 19. So 11 is just a special form of 19. So let me write this way. So as in the table here, it says that Laplace transform of minus t to the n times f of t is equal to the nth derivative. Yes. Or if you want, I mean, you can put this minus 1 to the n here. It's up to you. So the book wrote this way, so I'm writing. So it means multiplication with t means derivative in the S domain. So that's the reason, like, I mean, so until now, we didn't know anything about 1 over s minus 1 square, for example. So if you look at the Laplace transform of s minus 1 square, inverse Laplace of s minus 1 square. So inverse Laplace of s minus 1 square. So what is happening here actually? This is the minus 1 times the derivative of 1 over s minus 1. So what do we have here is the following: inverse 1 over s minus 1's derivative. Okay. Be careful, I'm taking derivative not in the time domain, I'm taking derivative in the s domain. So derivative, if you compute this, you get 1 over s minus 1 square with a minus. So what you have. So I can put minus out, inverse of this, and so we have 1 over this. Okay. Oops. What am I doing? So this thing says that you took derivative in the s domain. So if you take the derivative in the s domain, so then it will be equal to multiplication with minus t in the time domain. So minus t e to the t. Because e to t's Laplace is 1 over s minus 1. If you take its derivative, that means in the time domain, multiplication with minus t, and there's another minus here. That's coming just from this one. So that's the reason this is what we get. So taking the derivative in the s domain will correspond to multiplication with negative t in the time domain. So this was the last thing I would do in the second lecture. So if you look at the table as I mentioned here, like the properties of Laplace transform and also Laplace of certain functions, we did number 1, we did number 2, we did number 3. We are leaving the number 4 as an exercise for you if you are interested in gamma function. We did number 5, 6, 7, 8, 9, 10, 11 also done. Also 19 is done, 18 is done. So all these things are done. What is left is just 12, 13, 14, 15, 16, and 17. So that's what we are going to do. And the remaining of the sections will be basically about these things. And what did we learn in this lecture? You can solve differential equations or basic initial value problems by using Laplace transform. But power of Laplace transform basically comes when you have forcing functions are this piecewise continuous. That's what we are going to see in the upcoming lecture, where we are going to start with the step function and then apply it to solve certain differential equations. Okay. See you in the next lecture.